My name is Grace, and I'm a researcher at the Reality Labs research group at Meta. And I'm excited to tell you about some of my work and also cover some work of some of my colleagues on tackling the problem of incorrect perspective in VR pass-through. So, virtual reality pass-through is when we use external cameras on the front of a VR headset to show images of the real world to a user in VR. And this is going to let us interact more naturally with our surroundings. However, these pass-through cameras on the front of the headset capture a different perspective of the world than what you'd see if you weren't wearing the headset. Ideally, we'd place the cameras directly at the user's eye location, but we can't do that because obviously your eye is there, and then also the view of that camera would be blocked by the headset itself. Even if we place the cameras directly in front of your eye, there's still an axial displacement due to the thickness of the headset. So what this means in practice is that if we stream the images from that camera directly into the headset, it's not going to look quite right. So if you reach out to grab something, it might not be exactly where you expect it. And also when you rotate your head, those cameras on the front of the headset are going to move at a different rate than your eyes do naturally. So you're going to see different relative rates of movement between objects at different depths than what you would see without the headset on. Of course, all of this is relative though, and intuitively you can probably guess that if there's a large displacement between the cameras and your eyes, there's going to be more visual discrepancy, and the closer the cameras are to your face, the less this is going to be noticeable. So before I go too far into talking about how we can correct for this displacement, we really should figure out how much displacement is okay, and if this is really a problem we need to worry about for the distances we expect in a realistic headset. So my colleague Phil Guan tackled this question running a perceptual study on the requirements for world-locked rendering in VR, and his results are directly applicable to this problem of pass-through camera location. So in this study, basically what Phil did was he created a system where we know with really high accuracy where the user's eyes are at all times. The first part of this is this calibration rig where we align an individual user's eye relative to a byte bar, and we do this with this sort of complex camera system. And then we can take that customized byte bar and put it into a rig like this. So in this rig, users can rotate their head along one axis, and there's an encoder in this system that lets us accurately track that movement. And combined with that byte bar that I just described, this lets us know with really high accuracy where the user's eyes are all the time. In addition, there's shutter glasses here that are synchronized with this large screen TV, which allows us to show different content to the eyes and create like a 3D scene. Importantly, there's no lenses in this system between the user's eyes and this display, which means that we're not inducing any optical distortions that we're unaware of. So in the system, we can display a 3D scene, and we're going to render that scene before we display it so we know what to show. And when we render the scene, we can render it based on the known locations of the eyes, which we're tracking. This mimics that situation of an ideal pass-through where the cameras are co-located with the eyes. But in this rig, we also have the ability to change those render camera positions in arbitrary ways, mimicking the idea of having those pass-through cameras somewhere different. And so then, of course, once we have this set up, we can do studies where we can ask users if they can tell the difference between cameras located at their eyes and located further away. And that helps us start to figure out how far away we can place those cameras without users noticing a difference. So let's look at some results. So this is a plot from Phil's paper from last year. And as you move up on the plot, it represents moving those pass-through cameras forward towards the world. Moving down on the plot is moving them backwards towards your head, and left and right represent lateral translations of those cameras. Each of these circles here represents one user in the study, and the way to interpret this plot is that inside of each of these circles, that user was not able to distinguish between when the cameras were offset and when they were exactly at the eye. So what does this tell us? Well, for pass-through, the cameras have to be in front of the face, they can't be inside the head, so we mostly care about the top half of this plot. And we can estimate a threshold of about 15 millimeters, where we're saying if the cameras are closer to your face than 15 millimeters, then the users aren't going to be able to notice. But if they're further away, users can tell the difference. So unfortunately, even with headsets getting thinner and thinner, they're never going to be thin enough to place the cameras within that 15 millimeter range. Even a regular pair of eyeglasses usually has an offset of 18 to 20 millimeters from your face just to give comfortable eye relief. And so this means that even with future headsets, this visual displacement is still going to be a problem. So the natural next question is, can we adjust this camera position computationally after the fact? Let's put the cameras where it makes sense to on the headset for all of the other design choices, and then let's try to move that viewpoint computationally. This is basically a view synthesis problem where we're trying to generate a novel view at the eye location. And we just had a great plenary talk on NERF and all the ways that view synthesis has gained a lot of traction in the last few years. But in the space of pass-through, there are a lot of restrictions. Specifically, this needs to be done in real time, not just the rendering, but also the reconstruction part. And also, ideally, it would be something we could do on mobile hardware. So the first computational pass-through algorithm that met these requirements was this paper called Passthrough Plus from 2020. And the basic idea is we're going to estimate the depth of all the objects in the scene, and then we're going to warp the pixels based on their depth. So there's two challenges that you have to tackle when doing a computational pass-through approach like this. So first, you need an accurate depth estimation, which can be challenging. And second, there's missing information at occlusion boundaries. So imagine you hold your hand in front of your face. There's going to be things you can see between your fingers that the camera might not be able to see because it's blocked by your hand. And so that missing information needs to be filled in somehow. So Passthrough Plus takes an interesting approach here where they actually estimate a really smooth, low-resolution depth map, and that improves speed and power consumption. And it means that that missing information sort of gets filled in by warping the background to fill in those gaps. So this is pretty efficient, but it creates some sort of interesting artifacts. So here's an example of pass-through taken on the Meta Quest 2 headset, which is a version of the Passthrough Plus algorithm. And so you can see there's this sort of warping of the background around my hand when I wave it in front of my face. And this is characteristic of the design trade-offs that were made in Passthrough Plus. So this allows us to do a pretty good job of displaying the environment for things that are more distant, but especially at those boundaries between near and far objects, there can be a lot of sort of visual warping. So on our team, we wanted to see what computational pass-through could look like if we designed our own custom hardware and applied modern machine learning to this problem. This was a project led by my colleague Lei Xiao called Neural Pass-Through, and there were two components to this project: new sensor design and placement, as well as a new algorithm for pass-through. This is a picture of the headset that Lei designed. I think it looks pretty cool. It's got two high-quality RGB cameras that he did some calculations and determined that it was best to have them centered in front of the eyes, as opposed to in a commercial headset where those cameras the locations might be chosen based on a bunch of other design constraints. We also added depth sensors to this to try to help with the depth estimation problem. But research is all about learning something new, and one thing we learned from this project is that modern stereo depth estimation from just the RGB cameras outperformed the depth sensors that we'd chosen, so we didn't actually end up using those depth sensors at all. So updating the camera hardware is important to achieve better image quality, but if we want to remove those sort of warping artifacts, we need a new algorithm. And so at a high level, this algorithm that Lei proposed estimates a high-resolution depth map and then in-paints missing pixels where necessary instead of smoothly warping the image. So it basically starts with a pair of rectified stereo images from the two cameras, and then we're going to estimate depth from each input using RAF stereo. Then we can reproject those input images into the target view using forward splatting. And in this example, we're synthesizing an image for the left eye, but we applied that forward splatting to both input images from the left and right cameras. And this is good because you'll see when we do that forward splatting, there's black regions in these images, which are these disocclusion regions that you can see with your eye, but the camera couldn't see. And since we applied this to both cameras, a lot of those regions are filled in by the other camera. So most of these holes we can fill in with the other viewpoint, but there's still some regions that aren't seen by any camera at all. And this is a really fundamental problem in pass-through, is that there simply is information that's not captured. So in this algorithm, we proposed using a depth-assisted anisotropic low-pass filtering method, where the core idea is that we're going to use just neighboring pixels from the background to fill in those regions. Finally, we can fuse together those two images from the left and right cameras, and that's what we're going to display. So here's a cool picture of Lei wearing the headset. It shows that it really works. It all does this in real time, and you can interact with small-scale items like these chess pieces. And this is, let's see. Oh, it doesn't play on its own. Okay, here's a video of what it looks like. Oh, I remember. There was some problem with this video. Well, you can see in very small clips what this looks like when it plays. And it doesn't have any of those warping artifacts that we saw in Quest 2. There is some temporal flickering around the boundaries of objects, and that's something that we're working on improving with better temporal consistency in the depth maps. But I think this shows a lot of progress and shows that there's a lot more potential in what we can do with computational pass-through. But at the end of the day, computational pass-through is always likely to have some artifacts. First of all, depth estimation isn't always a very well-posed problem, and view-dependent effects are things that are pretty challenging to estimate from a limited number of views. In addition, as these algorithms become more complicated, that compute time adds latency into the system, and that's going to make it harder to interact with objects naturally because of the added latency. So it would be pretty advantageous if we could put the cameras at the correct position optically, so we don't need to do any of this computation. We can sort of sidestep all of this view synthesis algorithm. And so I'll pose to you a little challenge. So let's go back to this diagram, and we'd like to capture the rays of light that go into the eye. And let's say that you have some mirrors and a camera. How would you arrange them so that you could capture this image? Now, we don't have that much time in this talk, so I'll tell you someone else's solution. So this was a design that Henry Fuchs proposed in the late 80s, which was to fold the optical path using these mirrors to a camera that's above the head. And this allows us to capture those exact same rays that would have gone into the eye. So we can just stream that camera image directly into the headset, and it should look like that image was taken at your eye. Now, you can probably see already some of the challenges with this. It's really bulky. Adding in that 45-degree mirror extends the track length of the headset, and the field of view is pretty limited. And to make the field of view larger, you have to make all of these mirrors larger, and it becomes pretty unwieldy quickly. But it's a pretty useful, what we call time machine, to try to see what pass-through would look like if you solved this problem. And we are interested enough in this that it'd be really cool to try this headset and get the visual experience of what it's like. But I would be pretty surprised if Henry still has this headset from the late 80s. So on our team, we decided to build our own version of this. We made a few different design decisions, but here we have these two cameras that are sort of on these stalks and are pointed at a mirror on the front of the headset. And just like Henry's design, we are going to capture the exact same rays of light that would have gone into the eye. And so you can see that's what we're doing with this configuration. And this lets us see what perspective correct pass-through could look like. It's really silly looking. It's sort of, you've got these lollipops in front of your face, and it leads to some pretty strange social interactions if you're trying to have a conversation with someone. But it gets the point across. And so here's a video where the inset shows the perspective correct pass-through, and it gets toggled on and off compared to a computational pass-through algorithm. And this was really interesting enough that personally and as a team, we wanted to pursue this more. So can we make this sort of optical perspective correct pass-through in a practical form factor that actually seems amenable to a VR headset? And I probably wouldn't be asking you this question if the answer was no. I just so the answer is yes, and that's what I'd like to spend the rest of the talk discussing. So we did this with this design that we refer to as light field pass-through. It's inspired by a light field camera, if you're familiar with that technology, but it's tailored specifically to the problem of VR pass-through. So we wrote a paper on this last year, but you don't feel obligated to go read it because I'm going to try to explain it to you now. So we start with this idea of a light field camera that consists of an array of lenses in front of a sensor. And this isn't what our final design is going to look like, but it's a useful starting point. So just like in those other designs, we'd like to measure the rays of light that would have gone into the eye, and the eye is located some distance behind the sensor. So if we wanted to do that, we can approximate our target image by choosing the pixel on the sensor that corresponds most closely to the ray bundle of interest. If we do this over the whole image, we can build up sort of our final image by selecting those pixels that are most similar to the ray bundle we want. And you can see at some locations, we exactly measure the ray bundle that we wanted, but at other locations, specifically at the boundaries between lenses, there's more discrepancy and there's this visual jump between the lenses. So if we do this in practice, Here's an example, which is a simulation. And at first glance, this just sort of looks like a normal image. But if you look closely, especially on that purple ball, you can see that there's sort of these discontinuities. And these become more severe as we move closer to an object. So the nearer field an object is, the more pronounced those discontinuities become. The challenge here is we'd like to select a subset of the rays hitting each lens. Here, we'd like to select about half the rays from one lens and half the rays from its neighbor. But for each of these lenses, it's kind of all or nothing. So our key design insight for this project was to add an array of apertures, one behind each lens, that physically block all of the rays that wouldn't enter the eye. So here, I'm going to highlight the rays that reach the sensor, and you can see that we're now able to measure just half of the rays from one lens and half of the rays from their neighbor. And not only that, they're exactly the rays we wanted to measure. We can design these apertures so that this works over the whole field of view, and we're able to accurately measure those rays that are going into the eye at all times. So this is an example of one of these lens array prototypes that has the lenses in the front and the apertures in the back. And if we design this correctly, you can see that there's this single circle that looks like it's somewhere behind the array. This isn't the case. There's actually one tiny aperture behind each of these lenses. But that circle represents the center of projection of this camera, and that's where we're going to place the user's eye in our design. We can take our aperture array like this and put it in front of our sensor, and we capture an image that looks like this, where each of these lenses is capturing a different subset of the field of view. Then, to form our image, we're capturing all the data we want, it's just in the wrong place, so we simply need to rearrange these subviews to form our final image. So this is super fast, it's just a pixel rearrangement function, so it can be done with really low latency. But there were still some issues with this image, and what we realized was happening was that there was a view dependence to the calibration about how we move those pixels. And so this image has the calibration at optical infinity, but if we move that calibration plane closer, you'll see that when the calibration plane is close, foreground objects look best with fewest artifacts, but the background has a lot of doubling, and vice versa. So far away, there's the foreground sort of has some warping and doubling, and the background looks pretty good. So I don't really have time to get into why this happens. It turns out it's due to some non-idealities in the system. But we can estimate a coarse depth map using the overlap between the neighboring subviews, and then use that depth map to select the correct calibration that we want. So this helps improve that doubling artifact, but there's still another artifact that you might notice, which is you can see sort of the circle outlines from those individual circles. And that's due to stray light in the system. So light that's not supposed to be in a certain lens can bounce around in that lens tube and change the overall intensity of different subviews relative to each other. And that's what creates those seams. And so there's two ways to deal with stray light here. We can physically try to remove it through better baffling and better AR coatings, or we can try to computationally remove it by trying to do a more seamless stitching. And so at this point in the project, we had already built the hardware, so it didn't seem like a very good option to go and mess with it anymore. So we decided to implement a computational smoothing, which we did in a way that's similar to how panorama stitching is done. And it does a pretty good job of removing these seams, so you can see a lot of them get removed. Even with this smooth image stitching and the depth estimation, this algorithm is really fast, and we were able to implement a version of it in under 1.7 milliseconds per frame. In the end, though, we want to see this in action, so we built our light field pass-through architecture into a complete binocular prototype headset. So this version has 106 individual lenses. The user's eye is 35 millimeters behind the sensor in the design, and so we designed our aperture array to match that. Now this prototype was this sort of handheld demonstrator. It was a little awkward, but it was promising enough that it seemed worth it to do a major upgrade. We finished it about a year ago, and then we spent the next few months upgrading it to this version that we completed last summer. I think this new version looks super cool. It's fully head mountable, and since we got to redesign a lot of the components, we actually did end up adding in that better baffling. We added in better AR coatings on the lenses, and that allowed us to stop using that computational image stitching. And another thing that we added is we put in IR filters, which the other version was missing, which I'm a little embarrassed by. And you can see the IR filters add that very exciting red glow on the lenses. I think it looks really cool. So does this actually capture the right perspective? To validate this experimentally, we placed a camera at a reference position that would be where your eye is. And remember, we can't actually place a camera there in real life. And we can compare that image to what we'd get if we put the camera on the front of the headset, which is the closest point we could put a camera physically in the system. And so you can see the difference in perspective between what we want and what we'd get from that actual camera view. So now here's our light field pass-through reconstruction compared to the reference at the eye. And they aren't perfectly aligned because this was just an experimental setup, but it's pretty clear that our pass-through architecture is able to capture a perspective that's several centimeters behind the sensor. Here's another example, so comparing the camera at the front of the headset compared to what we want at the eye. And now comparing our light field pass-through to the view that we want. And you'll note that even for some pretty complex objects, like complex occluding structures, even this sort of prism paperweight thing, we're able to capture sort of the same viewpoint, because we're actually measuring the rays of light that we would have gotten from that camera. Here's an example taken through the lens of our headset prototype compared to a view of the scene without the headset there. And you can see that the view through the headset and the real world scene match really well. And finally, here's a video that showcases just the natural temporal consistency of light field pass-through. The image quality looks really good. You don't see any of that warping. You don't see temporal flickering, even though we didn't apply any specific temporal smoothing. This particular reprojection-based pass-through is a pretty old version from the Rift S, so it looks particularly bad. And we're able to do well even on objects that are challenging for computer vision, like things with specular highlights, view-dependent effects, or thin occluding structures. In the end, though, a video like that can only show so much about what this is like. We want to really improve the pass-through experience. And so this is a fully functional prototype. And so we could show it to a bunch of people and get their reaction about whether or not this technology was something that improved the pass-through experience. And we didn't just do this internally. We actually last year took this to SIGGRAPH, where we showed it to hundreds of people at the Emerging Technologies program. We got a lot of really positive feedback from people, and the headset actually won Best in Show, which I'm very proud of. But part of the reason we wanted to take it out into the world was to also get people's honest, constructive feedback. And that's going to help us inform next steps in the design. So one thing that came up a lot is that when we showed people this headset, we'd frequently hold up an object, like a marker or something, and ask people to try it and grab it, or to touch the top of it. And so some people would be able to very accurately hit the top of the marker, and other people would reach out and they'd be a few millimeters, maybe half a centimeter off from the marker. And so it seems as though there's some amount of customization that needs to be done per person. This headset was designed just for sort of a nominal human, where we chose sort of nominal human characteristics. And so this was a design choice that we made as researchers to try to accelerate the process. But showing it to so many people made me really realize that there needs to be some amount of customization. And this leads to a question of how much of that is something that we're going to do in hardware, potentially a physical IPD adjust, versus in software doing some more computational approaches to make it customized for individuals. The other question that comes up all the time is, do you think that this is something that's practical? Are we going to see this in future headsets? It looks kind of crazy. And of course, I can't really answer that question right now. Only time is going to be able to tell. But one of the things that I think is really exciting about this architecture is we're changing the design space. We took this problem that's historically been done software, computationally, and we're coming up with a solution that is less computational and more hardware heavy. And that has a lot of costs that you can probably think of. The whole thing's heavier, it's more expensive, it's just more hardware. But I do think that there's precedent of moving in this direction. So probably 5 years ago, you, like me, were all taking pictures with your cell phone, but that cell phone probably had one camera on it. And today, most cell phones have 2, 3, 4, I've seen ones that have crazy numbers of cameras on them these days. And those cameras are making your phones more expensive, it's making them bigger and heavier, it's making them more power hungry. But we've moved in that direction, and we've seen that both consumers and phone manufacturers seem to be interested in this. And I can say, for myself personally, I'd certainly rather use the 2x zoom lens on my new phone than have some sort of computational super resolution algorithm, because we're actually measuring the real rays of light, we're not making things up, and that image is just gonna look better. Now, I do think there's like a limit to this, right? Like, we don't see many people walking around with their DSLRs, even though they take generally better pictures than our cell phones. And so for whatever reason, whether that's cost or size or just how it's integrated into our lives, there's some point where we're no longer willing to like put in more hardware in order to solve a problem, at least in our everyday life. So I think we have yet to see whether this light field architecture is sort of in the direction of adding another phone on your cell phone, or if it's in the direction of a DSLR, which is still a useful item. It's still useful to be able to get a very high quality image in some applications, but maybe isn't the thing that's the consumer device that everyone's using every day. So hopefully though, like, I think that this architecture is something that at least opens new possibilities for how we can do pass-through in the future. So thanks so much for listening, and I'm happy to take any questions.